Okay, so so we've been building up a theory of boundary layer solutions, and just to recap so far what we've talked about, the general idea with problems that have boundary layers is that is that you can essentially start by solving the order 1 equation using sort of the first term of a regular expansion. And then from this, see if boundary conditions can be satisfied, okay? If some can't, then find an inner layer scaling, okay? And you can call that x, big X or something like that equals x divided by epsilon to the alpha. And you want to choose alpha typically to include any higher order derivatives in leading order expansion. And then the idea is that you want to solve the inner equation, satisfy boundary conditions, and then match to outer solution. And then lastly, make composite by subtracting off the common part, okay? And you got some practice doing this with sort of single boundary layer examples on your homework that you're turning in now. We talked some on Monday about higher order expansions and also examples of matching with boundary layers at both ends, nonlinear equations. I'm going to talk some today about reaction systems, multiple layers, exponentially small terms, and then maybe we'll start on what are called interior layers. And so, yeah, for the next several lectures, we'll just sort of build up these ideas on kind of variations on this theme of finding some inner layer, finding its solution, and then matching it to the outer solution. Okay, so so just to take a model that is common in reaction diffusion type systems. This is just the reaction system without any diffusion. The idea here is that our independent variable is going to be time. And I'm going to write down a model that's called the Gray-Scott model. It's a model that's commonly used in pattern formation and a lot of chemical and biological systems. And the idea is that you have two chemical species, for interesting, and they have this nonlinear reaction term. You have some source of one of the chemical species that's decaying, and sort of also linear transfer of one chemical species into another, and then the decay of another chemical species. This is called the Gray-Scott model. And it's a model of autocatalytic reactions. Okay, and we'll say that U at 0 is equal to V at 0 is equal to 1. And we'll have some initial layer then at t equals 0, okay? And so our outer solution is going to be for t greater than 0, okay? And this can happen for a lot of reaction systems. You have this initial phase where the reaction equilibrates rapidly, and then you have some slow evolution of the concentrations of your chemical species thereafter, okay? So just following the plan of action that we've followed before, we can say that, well, the outer solution, we're going to take some regular perturbation expansion. So V is approximated by this regular perturbation expansion, and use approximated by a similar one. In a few lectures, we're going to look at cases where you may have multiple time scales. And so each of these functions is actually a function of your normal time scale and then maybe some slower time scale that would help you to account for sort of long time scale effects that would not be captured by a regular perturbation expansion. Okay, so if we do this, then our U equation becomes what? Well, at order 1, we're going to get 0 equals e to the minus t minus u0 v0 squared minus u0. So we can just rearrange terms here, and we get e to the minus t over v0 squared plus 1 is equal to u0. Our v equation is going to be d dt v0 is equal to u0 v0 squared plus u0 minus v0, okay? So if we plug in now this substitution for u0, we get a nice cancellation. So we just get, this is equal to e to the minus t minus v0, okay? And we can solve this for v0 is equal to t plus a e to the minus t, okay? And so a will be some constant for matching. Okay. So that's our outer solution now, right? We can plug this in to get our U0 solution. So this is our outer solution. So we just need our inner solution, okay? Now we can make this scaling free for our initial layer or our inner solution, okay? I'll just jump ahead and say that if you take tau equals t over epsilon, okay, then you get sort of the right distinguished limit. So in this case, if we take tau equals t over epsilon, and u is approximately u0 of tau plus epsilon u1 of tau, v is v0 of tau plus epsilon v1 of tau, and so on. Then our expansion becomes the following for our inner solution equations: u0 prime plus so on and so on. We're just going to take the leading order equation, e to the minus epsilon tau minus u0 plus so on and so on, v0 plus the rest of the expansion minus minus u0 plus dot, and then we have v0 prime plus so on and so on. And then because of our change of variables, right, we've absorbed the epsilon from up here, okay? But we got a 1 over epsilon over here, so we're going to move an epsilon over to this side, and we end up with epsilon times u0 plus so on and so on, v0 plus so on and so on squared plus u0 dot plus dot 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 minus v0 plus dot dot dot. Okay. Now, what do we do? Well, the typical thing that we do if we have a hierarchy of terms, we just truncate to order 1 in this case. And notice at order 1 that the right-hand side of v0 is going to vanish, right? So in these sort of nicely separated fast, slow timescale systems, right? In the long time scale, we see that you sort of reach this quasi steady state of your U equation here. Okay, in the short time scale, right, the V equation is not going to change very much, okay, because it's sort of slow on this time scale. So this epsilon sort of sets the time scale for this U equation and tells us whether, which layer it's going to matter in, right? The dynamics of V don't really matter in the inner layer because they don't evolve on a fast time scale as U's dynamics do, okay? So then what we end up with, the leading order, is U0 prime is equal to 1 minus U0 V0 squared minus U0. V0 prime is equal to 0. Okay. We have our initial conditions now. So we have U0 of 0 is going to equal to I think I wrote down the wrong initial conditions. Yeah. All right. So yeah, we're going to use, I'm just going to tweak these initial conditions. U0 equals 0 and V of 0 equals 1. Okay. So U of 0 is going to equal 1. All right. So so our U0 of 0 is going to equal 0, and our V0 of 0 is going to equal to 1. Okay. No, sorry, I was right before. I had a typo somewhere. Yeah, we're just going to use, yeah, we'll use 1 for both of them. Sorry to keep going back and forth. Okay. 1 and 1 for our initial conditions. So our initial conditions are 1 and 1. Okay. And what we end up with, if we solve this, is that V0 clearly is just going to be a constant solution. It's just going to be 1. If I then plug that in up here, right, I see I just get 1 minus 2U0. So I get an exponential solution plus a constant. So I end up with U0 is equal to 1/2 1 plus e to the minus 2 tau. Okay. All right. So this is now our inner solution. Okay. And if we want to match, then what would we like? Well, we'll shorthand it. It works to shorthand it in this case. If I just take U0 of 0 is equal to capital U of infinity, and then V0 of 0 is equal to capital V at infinity. Okay. I have no free constant here, no free constant here. Okay. My only place I have free constants, right, are just here, right? So I can choose A so that I get the appropriate matching. Okay. And if I do that, then I have that V0 at infinity is equal to 1, because it's just a constant anyway. And then this equation here at t equals 0, I get A for V0 of 0. Okay. So A is equal to 1. Okay. And I have no matching that I can do for the U equation here. But if I check this, if I take the limit as as tau goes to infinity here, right, I get a half. And if I look back over here, right, in this limit, if I take t is 0 here, v0 is 1, then I get 1 over 2. So I do get a half. Okay. So I get for free that u0 of 0 equals a half, okay, which is equal to big U0 of infinity. So that works out. Okay. So now I have my my inner and my outer solution. Okay. If I want to draw these, right? Okay. I'll go ahead and draw my inner solution here. It starts out at 1 for U, and then I get this rapid decline down to a half in the inner layer, okay? And then my big U0 there, okay? So U0 is going to be equal to e to the minus t over little v0, which now I know is t plus 1 times e to the minus t. So t plus 1 squared e to the minus 2t plus 1. Okay. So I can rearrange this just a little bit. So I get 1 over t plus 1 squared e to the minus t plus e to the t in this case. So we see in the limit as t goes to infinity, this is going to go to 0, right? This term here, this is going to start to blow up, but it's going to be dominated by e to the minus t. Okay, so this term is not really going to take off very much. So we're just going to have sort of a much slower decline in the u variable here. Okay. And then for v, right, v starts out pretty constant up here, right? And then remember v0 here is going to be t plus 1 e to the minus t. So maybe we get like a little bit of initial growth, okay, but then over time, it's going to decline as well. Okay. So basically, the decay of V is eventually going to move all of our chemical species out of the system in this case. Okay. So just to write down a composite solution, okay, we can write this as U is approximately equal to U0 of T over epsilon plus U0 of T, okay, minus the common parts there, right? Which in this case is going to be, well, yeah, so we'll show that we have just the 1/2 is going to be the common part in these, okay? So we end up with U is approximately equal to a half e to the minus 2t over epsilon. plus e to the minus t over 1 plus t squared e to the minus t, okay? And by a similar logic, okay, v is just going to be approximately equal to 1 plus t times e to the minus t, okay? All right. So in actuality, what we should expect is sort of a slight rise and then a steady decay of this v term here. Okay. All right. So any questions about this example? All right. So you'll have a problem to practice this on for ODE systems on the homework. You can see here that for a pair of equations, the idea is similar. The challenge sometimes is in solving these first order equations. Sometimes you have to, use a couple of tricks in order to solve a pair of nonlinear differential equations. Okay. Now, one note here is that sometimes long time scales can sometimes disrupt this ordering, okay? And then that's when we have to use method of multiple scales, which we'll talk about later. Okay. Let's look at another example where we might have multiple layers. And if I can draw this right, so this is going to be an example where we have y, the function of x. This will be a boundary value problem here. And what's going to happen is we have this sort of dip here, okay? This sort of hook where I have an inner layer here and then kind of an outer inner layer here, okay? So I need to stitch together sort of two different compressed spatial scales. And this arises from the following linear but non-constant coefficient differential equation. X lives on 0 to 1, y 0 equals 1, y 1 is equal to 3, okay? And we need to deal with the hook region near x equals 0, okay? So as typically we want to do, we start with our outer solution, right? So we get y, right, x cubed y prime is equal to x cubed, okay? The solution that works there is y is approximately x plus c, and we could try and match either boundary condition. If we match the left boundary condition, we would run into trouble later. So let's start by going ahead and picking the right boundary condition. So in that case, we'll take c to be 2, and we'll get just x plus 2. Okay, we'll match the right boundary condition. Okay. Now, if we match the right boundary condition, then the problem left is the left boundary condition. So let's take xl equals epsilon to the alpha. And in this case, we're going to get epsilon cubed minus 2 alpha, okay, d2 dxl squared yl plus epsilon 2 alpha xl cubed dxl yl minus epsilon yl equals epsilon to the 3 alpha XL cubed. Okay, I'm going to label all these terms. This is term 1, term 2, term 3, and term 4 here. Okay, now in this problem now, there's going to be two distinguishing limits. Okay, limits where I get multiple terms to match. Okay, if I want to match terms 1 and 3, okay, I can do that by choosing alpha equals 1. Okay, because then this is epsilon to the 1, this is epsilon squared, this is epsilon to 1, and then I get an epsilon cubed. Okay, now that's really going to compress my coordinate. So I'll call that my inner layer. Okay, and that'll be, in this case, my decreasing portion. Okay, now if you didn't have like a numerical solution of this problem, okay, you might not have so much of a guide of which portion was decreasing, which portion was increasing. Okay, but you can still sort of reason this out from scratch, in that there's just two possible distinguishing limits here where I'm going to get matched terms, and then you can plug things in and see what happens in terms of your solutions. But a lot of times, you're building asymptotic solutions because you already know something about how the numerical solution is going to behave, and you just want to get a sense of the scaling for the particular regions of the problem that you're interested in, okay, which you could not get so easily from the numerical solution. If we want to match terms 2 and 3, we can do that by taking alpha equals a half, okay? And I'll just call this the regular inner layer, okay? And for that, we're going to get this sort of minimum value of our hook in this case, right? So if we follow the typical approach, then if I take the inner layer first, right, for alpha equals 1, what I end up with is YL prime prime minus YL, okay, is equal to 0. Okay, I get that at, if I solve this, right, I get YL is equal to A e to the minus x L plus b e to the xl in this case. For the alpha equals a half case, I have that xl cubed yl prime minus yl is equal to 0, okay? And I can solve this using separation of variables. So, so if I work this out, right, I get dyl over yl is equal to dxl over xl cubed. It tells me that log of yl is equal to minus 1/2 xl to the minus 2 plus some constant, I'll call it k in that case, right? If I exponentiate, then I end up with YL is equal to C e to the minus 1 over 2xl squared, okay? And yeah, maybe I should put a star on this or something like that. to distinguish it from the other one. Okay, right? So then this is my just my inner solution, and then my inner solution is given by this. And now I can just do, following a series of sort of matching and boundary conditions, right? I have that y0 equals 0 implies that a plus b is equal to 0. Okay. I also am going to have that because I need to match these, that in the limit as this gets large, right, this should vanish. So I need that oh, sorry, this should equal 1. Right. So I also need that b goes to 0 so that the e to the xl term does not blow up. Okay. So then that implies that a is equal to 1 in that case. Okay. And then I need to now match a e to the minus xl, okay, with c e to the minus 1 over 2 xl star squared, okay, with each other there. And as this goes to 0, right, this is going to go to 0 too, so they match automatically. So the next part is just to match this to the outer solution as well, okay? So this happens automatically, right? There's nothing I need to specify. But if I want to match this one to the outer solution, in the limit as this goes to infinity, right, I'm going to get just c. So I get that c needs to equal 2 in this case, okay? So I now have my inner solution, which is e to the minus x over epsilon, right? I guess I call this my inner solution. My inner solution is going to be 2e to the minus 1 over 2x squared. But now because it has a scaling of epsilon to the 1/2, I get an epsilon up top, okay? And then my outer solution is going to be just x plus 2, okay? So now to make my composite, I can just sum all of these up, right? And I end up with y is then approximately equal to x plus e to the minus x over epsilon, okay? Plus, and then because both of these are going to be 2 in the outer layer, I can just subtract off that additional 2. So I don't need that trailing constant of 2. So I get 2e to the minus epsilon 2x squared x over my whole domain here, okay? And yeah, over my whole domain. Okay. So so then essentially what I've done is as I've been able to stitch together these 3 regions in order to get my boundary conditions and my matching conditions satisfied. Okay. All right. Any questions about this problem? Okay. All right. All right.
Oh, real quick, why didn't we match 1 to 2 or any other combination?
In our distinguishing limits here.
Yeah, like to have both derivatives show up or something like that.
So I think what happens if you have that 3 minus 2 alpha is equal to 2 alpha, I guess that's what you're saying, then you would need that alpha is equal to 3/4. So if I did that, then I would end up with, this is 3/2, right? This is 3/2 here, but it would be higher order than this term. So my leading order equation would just be this. And I would just get that YL is equal to 0 in that case.
Okay.
So yeah, that would be like that's basically your intermediate layer that lives between your inner layer and your just regular inner layer in that case, right? Which we found the solution goes to 0 in that sort of intermediate region. Yeah.
Okay.
So you could do that, but it's not going to provide you anything extra for your solution in this case. And then you were asking, yeah, I mean, why not match like 3 and 4 or something like that? I mean, I guess if you took alpha to be 1/3, then this would be order epsilon, right? But then this would be order epsilon to the 2/3.
Yeah.
So you would just have, yeah, again, I guess you would get you would just get a term kind of by itself. So typically the distinguishing limit, you want to be able to match at least 2 terms in your differential equation. Because then you're ensured to be using the most information that you can from the original differential equation in order to build your solution.
Gotcha. And then the matching we get for free on the next page.
Yeah, so for the matching here, right? If I want to match the inner and the inner solution here, right? Then the limit as XL goes to infinity here, and the limit as XL goes to 0, both of these are 0, right?
Oh, gotcha. Okay.
So there's no specifying of constants to do, right?
Yeah.
But to match to the outer solution, I have to take C equals 2 in order to get right. C equals 2 comes from the fact that my outer solution is x plus 2, right? So if I plug in x equals 0, I'm just going to get back 2. And then my inner solution is this C e to the minus 1 over 2 XL star squared.
Yeah. Gotcha. I was taking both XLs to 0 and was confused, but yeah, definitely need to make one go to infinity.
Yeah.
All right. Thank you.
Yep. Okay. All right. So then, yeah, and then at 1 we have, or sorry, yeah, at 0 we're gonna match our left. Okay. All right. So yeah, so there, I'll just mention that yeah, I think it's in Holmes 2.3. There's another example on exponentially small terms. I don't think that there's I didn't really give you anything on that on the problem set, so you can read over that if you want. I think I'd like to maybe kick off the section on interior layers now, just to set us up for Friday's lecture. Okay, so let's move on maybe to this problem of what's called interior layers. Okay. Okay. And so, we've built up a theory of generating solutions on these boundary layers. And the idea is that, You solve for the outer layer first, and then depending on where you're having trouble matching your boundary condition, you build a boundary layer there to sort of stitch the outer layer solution to the boundary condition, okay? But sometimes you may have inner solutions may occur on the middle of domains, okay? And just as we have been doing with this section, let's just immediately jump into an example where this happens, okay? So epsilon y prime prime equals y times y prime minus y, okay? And I'm going to take this on the domain. X goes from 0 to 1. Let's take y of 0 equals 1 and y of 1 equals minus 1. Okay. And let's immediately try and get an outer solution. So y is asymptotically approximated as y0 plus some y1, so on and so on. So in that case, I get y0 prime is equal to y0, okay? And so now either y0 equals 0, okay? Or y0 equals some function x plus a, okay? And we're going to have to determine which best matches our inner solution, okay? So we may not have, you know, a clear candidate at this point, right? We could either have y0 equals 0 or y0 equals x plus a. So we're going to have to kind of locate where the layer is in order to solve this problem. And to locate the layer, it's good to recognize what our possibilities are, okay? And then there's 3 possibilities, right? I mean, we saw in the last problem that, of course, you can have sort of multiple layer problems, right? But let's assume that there's just 1 layer, right? So we could have the following. So we could have that y looks like this. We have a left boundary layer, okay? And in order to kind of connect things together, we need a solution that looks like this, okay? X equals 1. We could have a right boundary layer, in which case we have a solution that kind of looks like this. In order to connect the 2 boundary conditions together. Or we could have an interior layer that looks like this, okay? So we have y kind of go up and then drop down and then rise back up again, okay? This is x equals 1, right? It's hitting the right boundary condition here, and it's hitting the right boundary condition here, okay? The correct boundary condition, okay? Now, before we just jump into getting an interior layer solution, let's show why we can rule out the left and right layer solutions, okay? Now, I think when I give you problems, I just tell you, well, you can just assume there's an interior layer, solve this problem as if there's an interior layer, right? A lot of these problems, sometimes when you're solving them for the first time, you have to try a left boundary layer, try a right boundary layer, and then if that doesn't work, try an interior layer, right? There's not always a crystal clear roadmap. It's just, run into some dead ends until you get a direction that works, okay? So let's say, what if there was a left boundary layer? Well, what we would need, and this is kind of how you rule it out, you would need essentially that the second derivative here, right, is concave up, So we should have that y prime prime is greater than 0. We also need that in that region, y prime is less than 0 because it's decreasing. And we also have that y is greater than 0 and y is less than 0 on that domain, okay? So if we look at our left-hand side, right, of our ODE, right, the left-hand side of our ODE, I'll call it star, is greater than 0, but the right-hand side, in that case, can be what? Well, if I look at this, right, whenever y prime is negative, right, and y is positive, then this whole part can be negative, okay? So the right-hand side can be negative in that region, okay, and it will be for this initial part, but the left-hand side is going to be positive. That cannot be so, right? So we can rule out a left boundary layer in that case, okay? By this argument, we sort of exclude that possibility. For the right boundary layer, okay, we have that y prime prime, right? If we look at the solution, what has to happen here, we need some part of this region where the curvature is going to be concave down here, okay? And we'll also have that y prime minus 1 is going to be less than 0. And also y can be greater than 0 and less than 0 along that inner layer. So that means the left-hand side is going to be negative, but the right-hand side can be positive. So that rules out the right boundary layer, okay? So this tells us that we have to build an interior layer because it's impossible to have a right or left boundary layer and satisfy our original differential equation, okay? Now, in the interior layer, what this tells us then is that either we need to take sort of y equals 0 for some part of it, or we need basically this jump discontinuity where we change the additive constant in that linear function, okay? So in order to get left of our layer, okay, at some place x equals x0, okay, we have that y prime minus 1 is less than 0, okay, y is going to be greater than 0, and y prime prime is less than 0, okay. If you look at this interior layer, right, we have a concave down solution. It's decreasing, and y is going to be positive for that part, okay. Right of x equals x0, we're going to have that y prime minus 1 is greater than 0, y is less than 0, and y prime prime is greater than 0, okay. And so this means that y of x0 needs to equal 0 in this case, right? Because we're going to switch signs as we go through that interior layer, okay? So this is going to guide our analysis in this case. And our approach then is going to be to choose some scaling. We're going to take x bar is equal to x minus x0 around this interior layer point divided by epsilon to the 1/2. X0 is going to live somewhere from 0 to 1, okay? And then we are going to have to do matching to now 2 outer regions, okay? There's going to be one outer region from 0 to x0 and one outer region from x0 to 1, okay? So we'll wrap this up on Friday, but the idea is, from henceforth in the problem, the analysis is quite similar from before, right? We look for the distinguishing limits of alpha in this case. We solve our interlayer solution. We hopefully have 2 constants so that we can match the left and the right outer solutions, okay? We choose our outer solutions now so that they match the boundaries appropriately, okay? And then we form a composite solution by subtracting off the redundant parts, okay? All right, so that's the idea with interior layers. We should be able to kind of wrap that up on Friday, and then potentially get through what are called corner layers, where you have discontinuities in your derivative that you want to try and smooth over. Okay. So any questions about this interior layer method or anything else from the lecture? All right. Okay. Well, that's it for today. As I said, we're kind of following along in the second chapter of Holmes. So if you want to read ahead, you're welcome to. But as with the rest of the class, there's kind of supplemental readings that I've given on the calendar. So if that's useful, I should have the next homework posted by later today, and that'll be due in 2 weeks. And the other thing that's due in 2 weeks is just to send me a proposal for your project as outlined on the syllabus. So let me know if you want to chat, if you need help sort of picking out a project topic that's appropriate. And yeah, otherwise I'll see you on Friday.
Thanks, Zach.
Thanks.